Hey guys, welcome. Yeah, so this is the first of many fun, challenging derivatives that we'll work on. So let's get on with it. Now, when you have x as a base and as an exponent, or in general, when you have a variable base and a variable exponent, then what you want to do is what's called logarithmic differentiation. And so this is a nice basic example on logarithmic differentiation. To start, we say y is equal to x to the power x. And this is where logs come in this next step, which is we take the natural log of both sides, and we see that we can write next the natural log of y, so the natural log of the left side, is equal to the natural log of the right side, so the natural log of x to the x on the right side, right? But wait, we have what's called the power rule for logarithms, and I have many videos on logarithms, including proof of the properties, so watch those, they're great videos. But yeah, anyway, using what's called the power rule for logarithms, we can write this exponent x in front right here. So this is what I'm saying. We can write this instead of what we had. Yeah? Okay, cool. Now we take the derivative of both sides and we do the differentiation implicitly. So we do implicit differentiation. And again, I have many great videos with some really fun problems on implicit differentiation. So check those out. Okay, now, so proceeding with the implicit differentiation, on the left side, we'll get the derivative of the natural log of y is 1 over y times, by chain rule, the derivative of y, which is dy dx. And remember, what we're after is dy dx. So from here on out, the name of the game is solve for dy dx, which is right here. But we have to continue with our implicit differentiation, so we go equals, the derivative of this right-hand side requires product rule. The product is between f here and g right here. So we have f times g, where f again is x and g is ln of x. And we know that that's supposed to equal, the derivative of f times g is supposed to equal f prime g plus f g prime. And I have examples of the product rule for derivatives, as well as the proof of the product rule and the quotient rule for derivatives, so check those out. Yeah. Okay. So, f prime g plus f g prime. F prime is 1. G is ln of x. That's the f prime g plus f g prime. So x, and then the derivative of ln of x is 1 over x. Yeah? Okay, cool. Now, I can multiply both sides of this by y, because as I said, the name of the game was get to dy dx. And all I have left to do is clean up on the right hand side, and we are done. And by clean up, I mean 1 times ln of x is simply ln of x, and then x times 1 over x is 1, and all of this is multiplied by y. But y was x to the x, so all of this, which is this, is multiplied by y, meaning multiplied by x to the x. And voila! So we have found the derivative of x to the x, which is this here. We have found the derivative of y, but y is that, and so yeah. Yeah? Okay, cool, cool, cool. So next, we'll look at the derivative of x to the x to the x. Okay. Yeah, so in the first part of this fun, challenging derivatives video series, we answered the question of what is the derivative of x to the x? And using the same approach, that is using logarithmic differentiation, this time we're going to answer the question of what is the derivative of x to the x to the x? Yeah? Okay, cool. As I just said, we're going to use the same approach as part 1, and that is logarithmic differentiation. So we start by saying that y is equal to x to the x to the x. Yeah? From this, we see that upon taking the natural log of both sides, we can write the left side is the natural log of y, and the right side is the natural log of x to the x to the x. Got it. Now, I have lots of fun videos on logarithms, including proving the 3 important log properties. And one of those properties is what's called the power rule. And it says something like the log of any log, not just ln, but yeah, the log of x to the power b is the same as b times the log of x. As I said, I proved this. So check that out. But yeah, notice here on the right side, b would be this here. Yeah? Okay, so then using this property, we can next write that what we had in the previous step is the same as saying the natural log of y is equal to x to the x times the natural log of x. Okay, now we knew to take the natural log of both sides of this to start because we want to bring down variables from the exponent. So what logarithmic differentiation allows us to do is it allows us to get rid of variables in the exponent. It doesn't make them exponents. Or yeah, you get it. But yeah, we still have a variable in the exponent here. So then we take the natural log again on both sides of this so that we can make this variable not an exponent. Bad syntax maybe, but like kind of didn't know how to say that well. So yeah, anyway, on the right side now we have the natural log of x to the x times the natural log of x. Cool. Now another log property which I prove in my log videos is what's called the product rule for logs. It says the natural log, and in fact the log of a times b is equal to the log of a plus the log of b. And I'm not using absolute values around the log argument because, well, I'm assuming that you know that logs don't take negative arguments. But anyway, this rule here is called the product rule, and we can apply it in this part because, well, we've got a product between this and this. So then next we can write the natural log of y, the left hand side here, is equal to the natural log of x to the x plus the natural log of x. So I'm saying over here a is x to the x and b is natural log of x. So we get natural log of a plus natural log of x, where natural log of x here is b, right? And this here is a. Yeah, okay. But notice that in this part I can apply the power rule for logs one more time. And so I can put the x that was an exponent right here, and that's the whole reason why we took the natural log of both sides of this here to write that anyway, right? So that we can bring this guy down and in this part, right? Okay, you get it. And now we're ready to take the derivative on both sides, so we're ready to do implicit differentiation is what I'm saying. Okay, fine. So when we take the derivative of this left side, well, the derivative of the natural log of anything is 1 over anything, so we get 1 over the natural log of y, but then by chain rule we need to multiply this by the derivative of this here, which is 1 over y, and then by chain rule we have to multiply by the derivative of this here, so the derivative of y, which is y prime or dy dx. And remember, what we're after is dy dx or y prime. Cool. So this here equals, and I'm going to have to continue on over here because, well, you imagine that this is going to be a little bit of writing. Because first, in this part, well, we're done taking the derivative of the left side. That's this. But yeah, when we move on to taking the derivative of the right side, because we're doing implicit differentiation, so we have to differentiate on the left and on the right. But yeah, when we come to the right, we first encounter this, which requires product rule. There's a product between x and the natural log of x. So applying the product rule, we write 1 times the natural log of x plus x times the derivative of the natural log of x, which is 1 over x. But this here is only the derivative of this, so we need to go plus and skip on over here and do the derivative of this, which is 1 over the natural log of x, but by chain rule we need to multiply by the derivative of natural log of x, which is 1 over x. Yeah, okay, cool. Now I don't need this anymore, and I'll try to fit it all over here. Okay, so it's clear that to get dy dx by itself, which is what we want, what we need to do is multiply on both sides by the natural log of y times y, right? But first maybe we clean up over here. No, it's fine. we can clean up, meaning like, you know, turn x times 1 over x into 1 and so on. So we could do that while at the same time multiplying by y times the natural log of y on both sides. So again, we multiply by y times the natural log of y on both sides, and on the left we just get dy dx equals, on the right I'll lead with y times the natural log of y, the thing we're multiplying by on both sides, times, and then here we have the natural log of x plus 1, and then plus 1 over x times the natural log of x. Okay, couple of things. One, notice y is x to the x to the x. Also, the natural log of y is the natural log of x to the x to the x, which, you know, as we said earlier, we can write the natural log of y as x to the x natural log of x. And in fact, I prefer to write it in this form, so that's what I'll do on that part, which is this part. Right, so I'm saying dy dx is equal to y, again, is x to the x to the x, right, that's y, and then natural log of y is x to the x times the natural log of x. But remember, everything I was going to write here, including the natural log of x, that I have to write right there, so that in this part I have natural log of y, right? But yeah, everything I write right here is going to multiply both this, well, all three things inside the parentheses. That's a better way to say it. In particular, this natural log of x right here is going to multiply all three of these guys inside the parentheses, so I'd rather have him inside the parentheses and keep these guys outside the parenthesis. And that's because when I put the natural log of x, this part of the natural log of y, inside the parenthesis, it's going to make this guy the natural log of x all squared, and that's going to be plus the 1 is going to turn into the natural log of x. But then what I wanted it the most for, distributing this part to the parentheses, is so that I can cancel this natural log of x here and just get 1 over x in this part. Yeah, I think that makes our answer a bit cleaner and nicer, but we are done. In the next part, we're going to do the derivative of x to the 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 x ad infinitum. Yeah, okay. Keep watching. I hope you enjoyed this. In part 3, we try to figure out what the derivative of x to the x to the x to the x ad infinitum may be. And just as we did in parts 1 and 2, we're going to use logarithmic differentiation. So we start with saying y is equal to x to the x to the x to the x dot dot dot. And so then notice that what I just wrote allows me to write that y is equal to x to the y. And why, you ask? Because we said y is x to the x to the x to the x ad infinitum. But then this here, right, which is x to the x to the x to the x ad infinitum, is y, right? If y is this here, right, well, this here is also y, and so that's why I'm able to, yeah? Okay, and then next we take the natural log of both sides of this. So on the left side, we'll get the natural log of y. On the right side, we'll first write the natural log of x to the y, but by using what's called the power rule for logs, we can write this y right here. I have lots of videos on logs, so check them out. And then next we do implicit differentiation, so we take the derivative on both sides of this equation, and I have lots of fun videos on implicit differentiation, including like some really challenging and interesting examples towards the later examples, so check those out. But yeah, we do implicit differentiation, as I said, which means that on the left side I write 1 over y, and then by chain rule times dy dx. And I have videos on the chain rule also, including its proof. So check that out. The chain rule proof is really fun. And then here on the right side, to do the derivative, we have to apply product rule, because there's a product between y and the natural log of x. So y is like f, and the natural log of x is like g. Now we know the derivative of f times g is f prime g plus f g prime. So f prime g is going to be 1 over, well, sorry, just the derivative of y. This is not ln of y. So f prime g plus f g prime is going to be the product rule applied correctly on this right-hand side. My bad, guys. F prime is just dy dx, because that's the derivative of y. And then times g, which is ln of x, plus f, which is y, times g prime, which is 1 over x. Like that, right? Okay, cool. And next, I can multiply both sides by y. That way I can get rid of this 1 over y. So I multiply both sides by y, right? So what that means is that, well, I can get rid of this y right here and put a square on that y, and then maybe scoot this and then write a y right there. Yeah? Okay, and no longer need this parenthesis and this parenthesis. And next, since the name of the game now is to solve for dy dx, I want to subtract this from both sides and factor out a dy dx on the left. So if we do both, which we can handle, right? That's simple enough algebra. We can write dy dx and then times, we would have had this minus this. So for retaining this guy, we need to write a 1, and then minus because we subtracted this to the left side, and then it's going to be the natural log of x times y. So I'll lead with the y ln of x, right? And then on the right side, thereafter, we'll just have y squared over x, right? Okay, next, to get dy dx by itself, all that remains is that we divide both sides by this fella. So that amounts to, on the right hand side, writing y squared over x times 1 minus y ln of x, right? Okay. Now, remember, y is equal to x to the x to the x to the x ad infinitum, right? And so then our final answer is going to be dy dx is equal to x to the x to the x ad infinitum squared, right? X to the x to the x dot squared. That's the numerator. But squaring this amounts to writing x to the 2 times x to the x to the x to the x, right? So I'll write it like that. And then, of course, in the denominator, we still have this whole thing, right? I'll write x times 1 minus y is x to the x to the x dot, and then ln of x and over.